The academic year. My name is Sarah Cook, and I'm one of the faculty advisors for the Math Club. It's great to see you all here today. I'm sort of looking through your Zoom windows and your pictures, and I can see you. Hello, hello, hello. We're very happy to welcome Professor Stephen Miller from Williams College, who is a friend of the math department. He has many Michigan math t-shirts, it's true. He worked with us over the summer in our math course summer camp. We're always happy to have him help us there. And he likes to speak in the Math Club, and we love to have him give talks. So thank you very much, Coach Steve, for coming back to speak. And with that, I will introduce you. So Professor Stephen Miller is going to talk about why I love monovariants, from zombies to Conway's soldiers via the golden mean. And before he gets started, I do have to say this, I forgot. So John Conway was an amazing mathematician who invented a lot of really fun and interesting math. He was a really fun mathematician, and he passed away in spring of 2020 from COVID. And so what we've decided to do in honor of him and his amazing contributions is we've asked all of the Math Club speakers this semester to consider giving presentations that at least touch on some aspects of something that John Conway did. He was an extremely productive mathematician. So you're gonna notice that theme throughout the semester. Okay, take it away, Coach Steve.
Okay, so it is a pleasure to virtually be here. I hope to actually be there next year. I'm going to just start with two stories of John Conway. I was fortunate enough to know him when I was in graduate school to just give a little bit of a sense of what type of person he was. When the undergraduates at Brown were running a conference one year, he was one of the big speakers. And he adjusted his talk to bring into what he was speaking of results presented by the undergraduates earlier in the day. And it was just moving to see him adjust on the fly and take into account what the other students were doing. The other one is when you were a graduate student, you could actually play him in backgammon. And if you got to 100 points against him, he would switch positions with you and he would become a graduate student and you would become a named professor at Princeton. Do not play always to win. He played backgammon to have interesting games. Now, if you started getting close to 100, he played to win. But fascinating person, very kind, always there for graduate students, always in the common room and just there to talk math. And that's one of the things I just want to really emphasize, given how difficult these days are right now, is, let's try to be there for each other. Let's try as much as possible to talk to each other, see how we're doing, and see what we can do. So your assignment for today is to speak up. This is going to be as interactive of a talk as possible. There's a friendly cookie monster who will hopefully come when we get to the third part of the class, or the lecture. Okay. So I want to talk about zombies. You could, of course, replace zombies with the coronavirus, but that is too close to home right now. So we will do the classic zombie formulation. So if I ever get a coat of arms after being knighted, there will be a hammer on it because of the law of the hammer. And there's many different variants. I like the last one, short and sweet. If all you have is a hammer, everything looks like a nail. And there's a lot of ways to view this. One way is if you're really good at something, you find a way so no matter what they give you, you can treat it as something you know how to do, and then you use what you're good at. But a better way to look at it is if you have a hammer, go to the land of the screwdriver. If they could have solved the problem using a screwdriver, they're smart people. They would have done so by now. But if you have a new way of looking at things, you have a chance of making a real contribution. So in addition to math, I've written papers in accounting, marketing, economics, geophysics, statistics, sabermetrics. The list goes on and on and on, because I can take what they're saying and convert it into math and then apply some number theory which they may not have been aware of. And that's one of my favorite things to do, is apply number theory in strange settings. All right, so I want to give you the rules for zombie infection. So if you share two walls with infected people or more, you become infected, and sadly, once you are infected, you are always infected. So for example, in this initial configuration, the three red squares are going to be the initially infected ones. The white squares are the initially uninfected, and we want to see how this disease propagates. So this is the first row, second row, third row, fourth row. Anybody want to tell me a cell that's going to be infected in the next term?
In the top row, like to the side one, there's a cell.
Which is this one, this one?
That one.
Yep.
Yeah.
And another one that's going to be infected? So you got
one diagonal to it.
Yeah, third row, third column.
Third row, third column, and it's just going to be those two. So after one moment in time, this is where we are. Does anybody get infected after this?
Yes.
Okay, who gets infected?
The second row, last
second
column.
row. Second row, third column.
Or yeah. And then
Yeah.
diagonal from that.
And diagonal from that. Okay, so now the infection is spreading. This is not great. Anybody get infected after this?
Second row, second column.
Second row, second column,
In the top corner.
and top corner. All right, how about now?
No.
It's done now.
Okay, good. So at least the infection has stabilized. We have zombie apocalypse over here, and we have a nice corridor of safety. All right, so my question is, the first one is, can you give me an initial state of infection that ensures that eventually everyone is infected? And when you have problems like this, it is okay to use a smart-ass answer. What is the easiest configuration you can give me? You can infect whomever you want that will guarantee that eventually everybody's infected. The simple.
Infect everyone.
Infect everyone, thank you. All right, complete carnage and Armageddon from day one. We infect everyone. This is costly. On an n by n grid, that's going to cost us n squared infections, n squared agents. So the question is, can you tweak this a little bit and do just a little bit better? Not a lot better, just a little bit better.
Only
You
leave one
take away
square.
a corner square, or
So good. One is take away just one corner square. And now you have n squared minus 1. Okay, we've made an improvement.
You take away like
every other.
every other one.
Yeah.
Or what if you checkerboarded it?
Yep, checkerboard, every other. I actually like checkerboard because I wrote a paper on checkerboard matrices with Michigan students and then generalized it this year with other Michigan students. Of course, I chose really good colors, you know, scarlet and gray, as you can see here. So we have a wonderful configuration now where everybody's infected and it's a 50% savings. But it's still of order n squared. So if n is large, it's still a lot of infections. Can anybody do better than...
I
Diagonal.
yeah,
Only
like a
one way down
diagonal
the
through the
diagonal.
middle.
So that's
Okay,
just
so-
n out of n squared.
I am getting a lot of diagonals, which is now linear rather than quadratic. And you can see this beautiful animation where the infection just spreads and gets everybody. So this is a wonderful savings. All right, so now here's my question. What if you only infect n-1 people? Do you think it's possible to place them in such a way that you can get everybody?
Yeah, can you do like two diagonals that are like separated by a gap, but they both touch like a thing? I don't know how to describe it very well.
Okay, so what I'm going to try to do is a little bit risky. I'm going to stop the share. I am going to move to share something else.
Hi, Mike.
So it's not showing all of my windows. So this one that was hidden, which has what I want. I had just opened Microsoft Paint, so I could just, all right, no, I'll do it this way. Try one last time, I apologize. Here we go, there we go. So, okay, so now I have pasted your cell. What were you saying I should do for my infections?
Well, I'm not so sure of this anymore, but I was thinking like diagonal line starting from like the second column top row, like going down some amount.
Okay. It's okay if it doesn't work. You know, let's try things. You mean something
yeah,
like...
okay, yeah, like 4 maybe, and then like jumping down 2 and then having like 3 more.
Jumping down to like over here?
No, like below it. This doesn't work though.
Like
yeah,
over here?
Yeah, and then, yeah.
So it's not a bad thing to try. And if you try that, what you will see very quickly is, you know, we will basically, you know, have this all expand out. And so in fact, this will get us an entire block over here. And we'll get an entire block down here. And now these two will actually get us something over here as well. But unfortunately, that's all we get.
What about the square?
Oh, wait. And then we get this one over here.
Yeah. And then there's one on the other side of it. Yeah.
Yeah, and you
Not
can go
an
to the
entire
right as
fifth
well.
row.
And so this will keep coming down and get all of these, correct?
Yeah. It's like a bigger box, but not the whole thing still.
Right. So in the end, if you do the problem correctly, which is much better than doing it incorrectly, you get a giant rectangle, but not everything. Any other thoughts? Any thoughts as to how you might try to attack this problem?
Well, the thing about if you have n minus 1, you know that there's going to be at least one column, and I think at least one row that doesn't start out with any. And it seems like if you can show that it can't spread into that column that doesn't start with any, then you might be able.
So that's a great conjecture. So right now, there is nothing in this column, and nothing ever gets to that column. There is nothing in this column, nothing gets here. But there was also nothing in this row, and that row is killed, right? So it is able to spread into a row where there was nothing, and if we just take the transpose, we can spread into the column. But it didn't do both. So again, for problems like this, the best thing you can do is just do some examples and gain some intuition. What should your first value of n be that you investigate?
Like 2 or
1.
1. So if you start with n equals 1, this problem is pretty simple. All right? Maybe that's a small value. Let's try n equals 2. And if we go to n equals 2, how many choices are there for which cell we infect up to symmetry?
Just 1. They're all corners.
So it's not too bad to investigate the case n equals 2 directly. If we try, I didn't seem to switch. If we try n equals 3, it wants to write in red, so I'll let it. How many places are there for the initial infection?
2 essentially.
3.
3.
Oh, 3.
You could
Corner,
go in a
slide, and
corner.
center.
So you only have 3 initial choices for the first infected and then 2 for the next. And so by doing brute force, you can see without too much trouble, there's no way to do it when n equals 3. Now, what might you conjecture with this success or lack of success?
You can't start with like only one.
You can't start with n minus 1.
So that is an outstanding conjecture. It turns out to be true. And let me switch. People can see the screen again. I actually have an iPad that's working right now so I can see and make sure I see what you see. All right, so I'm going to introduce this wonderful idea called a monovariant. A monovariant is a quantity that moves in only one direction. So can anybody give me a monovariant related to yourself?
Your age.
Your age. Would weight be a monovariant?
Oh.
No.
I assume not.
No. And in fact, when you are a very young child, there's significant fluctuations in your weight, as well as when you get older and don't exercise as much. So a lot of quantities can move in both directions, but it turns out if you have something that moves in only one direction, it's often very useful. And so what we're going to look at here is the perimeter of the infection. So imagine that we have 2 cells that are infected here, and this cell in the middle is not infected. So that means this wall over here is an outside wall. It's a perimeter wall. I don't know about these walls over here, but they're not in play right now. This is an outside wall, and on the other side, this is an outside wall. When this cell becomes infected, we lose these 2 as outside walls, but we gain these 2 on top and bottom. So the perimeter hasn't changed. Instead of having 2 across, I could do, of course, up and down, but it's the same. I could do 2 next to each other. And when you do the calculation, I lose 2 outside walls, but I gain 2 outside walls, no change. And what happens if you have 3 out of the 4 sides infected? In this case, I have 3 outside walls that are lost. I gain 1 outside wall, so the perimeter decreases by 2. And of course, if all 4 walls are outside walls, then the perimeter decreases by 4. So what we know is the perimeter is never increasing. And if n-1 are infected, since the perimeter never increases, the maximum perimeter is 4n-1 or 4n-4. So does anybody have an idea of what the contradiction is going to be?
That's less than 4n?
It's less than 4n.
Yeah.
So as we said, the monovariant perimeter never increases. The perimeter of the square is 4n, so at least 1 square is safe. How do you view this theorem? Are you happy? There's at least 1 place for you to be safe. What would you like to know?
Where
that is.
Is it always the same place?
Where is it? Is it always the same place?
Or is it always the same kind of place? Like, is it always a corner?
Yeah, is it always a
side?
corner?
Is it always diagonal from an originally infected square?
But let's go back to one of the conjectures we had earlier. What was the conjecture that turned out to be partially false?
That something like a row or column can be infected even if there's no initially infected square there.
Right, so one thing is that the infection can actually jump and infect a row or column that was initially safe. But the initial conjecture was that there's, if your row or column doesn't have anything, you stay safe. And in the problem we looked at, we actually saw that there were 2 columns that were safe. So what might be a reasonable conjecture to make here? We know there's at least 1 square safe, but that's a lower bound.
At least a row or a column?
Yeah, is there a row or a column that's safe? Let's try to make our result twice as good. Can you prove that there are at least 2 cells that are safe?
Didn't we have the case where we were able to fill up the entire, there?
So we can, but this was when we assumed that initially we had a diagonal that was infected. That was n squares.
Oh, okay, so now we're not. Okay,
No problem. Now we're doing n-1. And so my question is, let's say this square is safe. Is it possible that this is the only safe square?
No, it'd be infected too.
It would be infected. And so it has to have at least one of its neighbors not infected. Now, of course, the one that's not infected could be in the middle. And so my question to you is, how far can you push this out? We know that there's at least 1 square that's safe. We quickly get there's at least 2. Can you prove that there's an entire column? I'm going to risk changing the screen that I'm sharing. And so when we go back over here, you see that there was an entire column that was safe. And what was the shape of the infected region?
Rectangle.
So is that a reasonable conjecture that the infected region is either a rectangle or a union of rectangles?
Yeah.
Yes.
Because I could give you something.
It's a good conjecture.
I could give you something like this, where this is infected over here, and this is infected over here. So it's clearly possible that it's not a rectangle, but a union of rectangles. So if you have a union of rectangles, is that enough to prove that you have a safe column? Or maybe you have a rectangle all by itself floating in a column. So I'll leave it as an exercise to see just how far you can push. But what I like about this is that by just knowing there's 1 cell that's safe, it actually pushes upward and gives you a lot more. Okay, so any questions about the first problem we looked at? So the hardest part about these questions is figuring out what is the right monovariant to look at. What is the right way to look at the problem? So, this is a picture of Conway. There are a tremendous number of things you can talk about. I would be surprised if at some point in the semester, I would be shocked if you don't hear at least one of these 4 items sometime during the semester of Conway. You know, the game of life, the monster group, audioactive decay, or the 15 and 290 theorems. Just he has a lot of very refreshing ways of looking at mathematics. And so here's an interesting problem. Imagine you have infinite checkerboard, and the pieces are at coordinates x and y, where y is less than or equal to 0. And so the way the checkers move is you can do vertical and horizontal jumps. So over here, I had this piece jump over the piece above and move up 1 unit. And when you jump over a piece, the piece is destroyed. I could, of course, have this piece move horizontally and destroy that piece. And the question is, how high can you move a piece? So this is a configuration that shows that you can move a checker up 1 unit. This is really not that impressive. Anybody have any thoughts about how you might be able to do 2 units?
You can yeah, go ahead.
No, yeah, go ahead, sorry.
Like you can like move checkers into the column where you're raising in the middle, and yeah.
So this isn't what you said. So this is what you said. You actually said I can move into, I think, columns where I have something open.
Yeah.
I actually moved 2 up first, and then I moved 1 over and then moved 1 up.
Okay.
There's lots of ways to move 2 up. So if I was teaching a class, your homework problem would be go home, can you do 3, can you do 4, can you do 5, can you do an arbitrary height? If you have 2 different solutions, how would you determine which solution is best?
One that destroys the fewest number of pieces.
Okay, so one way is the way that destroys the fewest number of pieces. I think that's equivalent to the one that has the fewest moves.
Yeah, it is.
Because each move destroys a piece. And so your spin is a much more positive spin than mine. Mine was, to move as few pieces as possible. Yours is to preserve as many lives of your soldiers as possible. All right, so I'm going to save some time, and I'm going to show that it is impossible to move a piece up 5 units. And the way Conway proved this is he introduced a really strange monovariant. And it's related to some of my favorite numbers in mathematics. This is a beautiful picture that I found on the web. I love how it's color-coded. And if you look very carefully, there's a big T here. That's the target that we're trying to get up to. So this will be the point x equals 0, y equals 5, 5 units above. And then we have a lot of values. We have x, x squared, x to the 4th, x cubed, x to the 5th, x to the 6th. Anybody have any conjectures as to how we're getting these numbers?
It looks like the same sort of deal as the zombie problem. I don't know exactly, but...
like you multiply together ordering numbers from the T, I guess.
So what do you mean by multi? So why is this an x?
Like, what I was thinking is that you just start with a T that is bordered by these 4 x's, and then you combine the 2 x's to get like an x squared in each of these corners.
Okay.
It's like the number of orthogonal moves away from the T.
Ah.
Yeah.
It is the number of orthogonal moves. It's the number of horizontal and vertical steps. That's the exponent of x. So if I multiply x and x to get x squared, how do I get the x cubed? It's not a bad thing to try. And so Conway's invariant was you put over here x to the power, which is the number of horizontal and vertical steps. And so this is x, x squared, x cubed, x to the 4th. This would be x to the 5th down here. And so what you can do is you can see how many pieces you have. Well, we start off infinitely, and you can see what is the value of the board. And then you can ask, as you do a move, what does that do to the value of the board? So what freedom do we have here? So I see somebody actually posted in the chat exactly what I'm asking right now. What is the freedom that we have here to choose?
maybe like the column in which we're trying to push for, like which side of the board we use?
Well, since the board is infinite, without loss of generality, I can assume it's the column corresponding to x equals 0.
Oh, I didn't know that. I thought
Yep.
it was just, I thought it was this many rows or this many columns.
No, due to budget cuts, I could only draw a finite analog of the board.
Dang.
I know. So what's the 1 degree of freedom we have right now?
Whether we do a vertical or a horizontal jump.
Well, that's our moves. But what I'm saying, when you look at the board and I put in the labels, what freedom do we have to choose?
Can vary x.
We can vary x. Now, if I want to look at what the initial value of the board is, do you want x to be greater than 1 or less than 1?
Less than.
Less than, because we have infinitely many pieces here, and the powers of x are getting higher and higher as you get further and further from the target. So clearly we're going to choose for x something less than 1. And if we choose x to be sufficiently small, the initial value of the board is going to be finite. And then we can see what does each move do to the value of the board. And if we show that each move does not increase the value of the board, well, we know over here this is a value of 1. And so if the initial value of the board is less than 1, we won't be able to get up to here. So that's the rough idea of the proof. We're going to show that the value of the board never increases. The initial value of the board is less than just 1 piece over here. Therefore, it can't be done. You can do a similar argument for 4 or 3, and it will come up that it is possible. It doesn't mean you can do it, but it means that the monovariant is not enough to disprove it. And in fact, there are ways to do moves of 3 or 4. They are deliberately not in the slide, so you can have some fun trying to do that. All right, am I allowed to offer money from Michigan professors for this, or do I have to do my own money?
You can offer money for Michigan professors. I offered money for my thesis advisor in class yesterday, so it's only fair.
All right, I will offer, but you can't use any resources. No cheating by using resources. I will offer $10 from Michigan professors, and I will match it with $10 of my own. All right, so our target point is 0, 5. And as we said, we're going to attach xi plus j to a point that is I units horizontally and j units vertically from t. So what's the value of the initial board? It's basically just a bunch of geometric sums. And so if you look at the first row over here, this is an x to the 5. We'll have 2x6s, 2x7s, 2x8s. So it's going to be x5 plus twice the sum of x to the k. K goes from 6 to infinity. Well, that's just a geometric series. And if you do the algebra correctly, which I did in my first edition of the slides, you get 2x to the 6th over 1 minus x, which simplifies to 1 plus x, x to the 5th over 1 minus x. Well, if you look at what happens to the next row, what's the value of the next row relative to the value of the row above it?
Even less.
X.
So if the value of the first row here is 5, what would the value of the next row be?
5x.
Multiplied
5x.
by
And the one under that would be
5x squared.
5x squared. So we just get another geometric series. So we just take this and we multiply by 1, by x squared, x cubed, and we sum that. Oh, well, okay, we know how to do that. And so when the dust settles, we get a value for the initial board of 1 plus x, x to the 5th over 1 minus x squared. Okay. So we have 2 types of moves. We can lose 2 pieces and add a piece that's further from t, or we can lose 2 pieces and add a piece that's closer to the target t. So the first type of move clearly decreases the value of the board. We lost 2 pieces and got a piece that was further away. So I don't even have to analyze what's going on in the first type of move. It's clearly going to lower the value of the board. What we have to worry about is when we have a piece jump and get closer. So we lose 2 pieces and get 1 piece that's closer. So for example, here is the case where I start off with a piece in the first row and the 0th row, and I jump and I get something in the second row. And so we had pieces on x6 and x5. We get a piece on x to the 4. So the change is x to the 4 minus x to the 5 minus x to the 6. we want this to be 0. Okay, well, I factor out an x to the 4th, and it's going to be a very simple polynomial to solve. More generally, it would be x to the n plus 2 and x to the n plus 1 is replaced with an x to the n. Instead of factoring out an x to the 4, I would factor out an x to the n. And you get the polynomial 1 minus x squared. So x is -1 plus or minus root 5 over 2. And so when we take the positive root, we get 1 minus phi, where phi is the golden mean. So what's wonderful is this is another strange place where either the Fibonacci's or their good friend, the golden mean, emerge. So if we choose phi to be, if we choose x to be 1 minus the golden mean, which is less than 1 in absolute value, then the value of the board never increases as the game progresses. So the initial value of the board, when we take that value for x, is about 0.76. If we have a checker at 0,4, the value of just that is 0.618. That's less than 0.76, so it is possible that this could happen. You don't seem to have that much to play with, but it is possible. If we have a checker, however, at 0,5, just that one checker contributes 1, and therefore it's impossible. We don't have to examine anything. And this is the power of the monovariant. It's extremely hard sometimes to find the right monovariant to look at. But if you can do that, it is absolutely wonderful what you can prove. It's a new tool in your arsenal, but it's almost more art than mathematics. It's trying to find the right way to look at something. All right, so I have had the fortune of working with Michigan students for many years in 2 different RUs this summer. One of the things I always tell my students is whenever you're given a problem, whenever you hear a talk, whenever you see a paper, you always want to talk about how can you generalize it? What else could you do? So these are open problems now, and I'm happy to talk to anybody who wants to try to convert this into research. How might you generalize Conway's game? What could you do next?
You could think about the 3D case where instead of a board of squares, you have like cubes.
Wonderful. You could think of the 3D case. And I've come close to buying the 3D chess sets from Star Trek to use in my multivariable calculus classes. Make this 3-dimensional. Would that allow you to go further? And of course, once you do 3-dimensional, what do you do next?
4.
4, and in fact, you do general dimensions. Okay, so that's one way to generalize. How else could we generalize?
Could you like put n squares, like have n squares away from, like a target n squares away, and how would you get there? Like, is that?
So if it's just one target, we can clearly do that by the fact that I know we can do things up to height 4. If I give you 2 things of height 4, though, do you think we can do that?
Yeah.
I don't know, because maybe we have to use certain pieces. And maybe they won't be available. So the game could become, if I give you a couple of targets, is it possible to get all of them? And maybe if I give you too many targets, it won't be possible. So which configurations? I see somebody in the chat just said, change the shape of the board. You know, what if we do this on a different kind of lattice? What if we do it on a hexagon? There's many ways you can push this. So let's see, I wrote different lattice, higher dimensions. I also wrote, what if we have some new types of moves? What if we can jump diagonally or jump over 2 pieces? So this was inspired by hyperradicals. Has anybody heard of hyperradicals? I think I saw one person shake their head yes. Or nobody has heard of them? Good, so if I get it a little bit wrong, it's not so bad. If you try to find a closed form solution to a polynomial, if I give you a quadratic, we all know how to do this. It's -b plus minus square root of b squared minus 4ac over 2a. There's a formula for the cubic. It's a little bit worse, but it exists. There's a formula for the quartic. It's even worse. There is no closed form solution for a general polynomial of degree 5 or higher. But I believe if you introduce something called hyperradicals, you can actually solve some of these. And so the question is, If I introduce new moves, what am I able to do now? What if I could jump over 2 pieces? That would change a lot of Conway's argument. And so then the question is, well, what happened in that case? Well, what if you choose if you want to remove the jumped piece? And so if the jumped piece stays, that gives you more to play with. So again, there's lots of different things you could do here. All right. Any questions on this one before we move to our final unit? All right, so the last is the Zeckendorf game. This is a game I created to play with my daughter a couple of years ago, and I gave it to one of my thesis students to analyze, Alyssa Epstein. So there's a lot of ways to define the Fibonacci numbers. I'm going to define them as 1, 2, 3, 5, and so on, where each number is the sum of the previous 2. And the reason I want to start 1, 2, 3 and not 1, 1, 2, 3 is a beautiful theorem of Zeckendorf. Every positive integer can be written uniquely as a sum of non-adjacent Fibonacci's. So 2020, one way to find this is to do the greedy algorithm. At every moment in time, subtract the largest Fibonacci number you can. So it'd be 1597, then 377, 34, 83, and 1. If you could ever subtract 2 adjacent Fibonacci numbers, then you were an idiot, because you could have subtracted their sum, which is a Fibonacci number as well. So it's a nice exercise to prove that every number has a unique decomposition, and that the decomposition does exist. Conversely, this is a way to define the Fibonacci numbers. So let's consider and construct a sequence so that every integer can be written as a sum of non-adjacent terms of the sequence. So we start with 1. I can't get 2, so I have to add 2. I can't get 3 because I can't do 1 plus 2, so I have to add 3. Can I get 4 as a non-adjacent sum?
Yeah. 1 and 3.
Yeah, 1 and 3, so I don't have to add 4. Can I get 5? No. Can I get 6? Sure, 1 and 5. Can I get 7? 2 and 5. Can I get 8? No. And so I'll leave it to you to just continue and show that this is an equivalent definition of the Fibonacci's. All right, so there's a lot you can do. I'm not going to really go into these slides. You can talk about which decomposition has the fewest number of summons. Monovariants play a key role here. You can talk about not just Fibonacci's, but more general sequences. I'm not going to go through the proof. I will leave it here so that you can always pause the slide or email me for the paper. What I want to do now is introduce the game. So it's a 2-player game. You alternate turns. Last one to move wins. And there are 2 types of moves. So we start off with a couple of bins, and the bins are the Fibonacci numbers, F1, F2, F3, etc. And you start with n pieces on F1. So if I give you the number 20, we start with 20 beads on the 1 bin. And then you can take 2 pieces on Fk and put 1 in Fk plus 1 and 1 in Fk minus 2. So for instance, if I have 2 8s, 8 plus 8 is 16, I can replace that with a 13 and a 3. If I have 2 13s, that's 26, I can replace it with 21 and 5. The only thing you have to be a little bit careful about is if you have 2 on the 1, then it becomes just 1 on the F2. And what's really going on is we have a 0 bin that's just not in the game. And then the next is if I have something at Fk and Fk plus 1, so say I have something on the 3 bin and the 5 bin, I can replace those with something on the 8 bin. You basically use the Fibonacci relation. So there's a lot of questions you can ask. Does the game end? How long does it take? For each end, who has the winning strategy? And the last is, what is the winning strategy? So let me just give you an example of a game. So we'll start off with 10 pieces at F1 and everything else is empty. So the first move, there's only one possibility. I have to take 2 on the 1 and put something on the 2. So now I have 8 pieces here and 1 piece here. And note, 8 times 1 plus 1 times 2 is still 10. I have 2 moves. I could take a 1 and a 2 and get a 3. Or I could take 2 1s and make a 2. I'll take 2 1s and make a 2. On this term, I could take 2 1s and make a 2. I could take a 1 and a 2 and make a 3. Or I could take the 2 and split. I'll take the 2 and split. And so that's going to become a 3 and a 1. And you can see 7 times 1 plus 1 times 3 is still 10. And so now I only have one choice. I have to take 2 1s and make a 2. I'm going to take a 2 and a 3 and make a 4, and so on and so on. So the game keeps going, and eventually player 1 won this time. And so here is a list of the game by the moves. Is anything jumping out to you when you look at this table?
The first column.
Okay, what about the first column?
It's always decreasing.
I thought it goes 6 to 7.
Oh, never mind. Missed
Like
that.
The sum of the numbers in the columns is decreasing.
The sum of the numbers in the columns is decreasing.
Yeah, that's not even true between F3 and F4.
But 6 plus 2, 7 plus 1, they're both 8. So modify, you're never decreasing. How do you modify it? Oops. How do you modify it? So when it's decreasing, that was too strong.
The
Decreasing or stays the same.
Number, the sum is the same.
Okay, so say that again.
Like you multiply the number in each column by the corresponding Fibonacci number and sum them together, it's the same.
Right, and that's because we are decomposing the number 10. So that will always be the same, but it's almost the case that the sum of the numbers in each row is decreasing. It's not quite. So instead of saying it's decreasing, what should we say?
It's a monovariant.
No.
It's a monovariant, but what monovariant?
Non-increasing.
Non-increasing. So we have something that's non-increasing. And in fact, you can prove that there is a monovariant, and you can prove that it will always converge to the Zeckendorf decomposition. I left a gap over here because over here, I took a 1 and a 2 and I made a 3. I could have taken the 2 and split it. And if I do that, that takes an extra move, and now player 2 wins. So there's a way to do a parity steal. And so you can prove that every game ends in finitely many moves. What you should do is, it took a while, but if you look at the sum of the square roots of the indices, it's a monovariant. There is a really good rule that you should never do too much algebra live in a talk, and I will follow that rule here and just leave it as, look at this, go through the algebra, look at every possible move, and you can show that it's never going to increase. There's an upper bound that it takes at most basically n log n moves that was recently improved this summer to just order n moves. We have an understanding of what is the fastest possible game that you can play. We actually looked at random games, and if you look at random games where you just take, well, whatever move I can do, I'll do, it looks like it's Gaussian in terms of how long the game is going to take. Now here is the annoying part. So I assigned my student, Alyssa, to tell me how to play against my daughter. And she came back and said, as long as n is not equal to 2, and when n equals 2, the only thing you can do is you have 2 things on the 1 that becomes something on the 2 and the game is over. As long as you're not in that case, player 2 has a winning strategy. It's non-constructive. So to give you an example of how bad non-constructive theorems are, imagine you are hired as a consultant for someone running for president. And you tell them, good news, we've proven you have a strategy to win the election and get the needed electoral vote. What do you think the candidate will ask you?
What's the winning strategy?
What's the winning strategy? And then you say, oh, well, actually, I'm a graduate of the University of Michigan. I'm a theoretical mathematician. It's a existence theorem. Now, it's nice to know that you have a winning strategy. That means, okay, I stay, I fight. But just knowing that you have a strategy, you know, do I concentrate my resources in the Midwest? Do I go to the Southwest? Which is nowhere near the Midwest, which, anyways, bad joke. So existence theorems are not always wonderful. So I'm going to highlight the fact that you can have existence proofs without constructive proofs by looking at a similar game that's a little bit simpler called Chomp. Has anybody seen Chomp? All right. So I see at least one person has. So the way it goes is you have a rectangle board, and whoever goes last loses. And on your turn, you pick a dot. Let's say I pick this dot over here, and you eat everything from this dot up and from this dot over. Why do you think it's whoever goes last loses?
Because if it were whoever goes, well, because then you could win just by clicking on the bottom left.
Yes. And so this is how I always remember which way the game goes, because if I can just move in the bottom left and eat everything, the game is very boring. So I'm going to prove to you that player one has a winning strategy no matter what the rectangle board is. There's only one case when player one doesn't have a winning strategy. Any thoughts on what that would be?
Just one dot.
Yeah, when you just have one dot. So we're going to ignore that. So let's prove player one has a winning strategy. So there's two possibilities. If player one has a winning strategy, player one should play it. If not, that means for this board, player two has a winning strategy, and player one is going to try to steal that strategy. So imagine player one goes here. And we are assuming that for this board, it's player two that has the winning strategy. So there is some place player two can go, which will continue their path towards victory. For definiteness, let's say it was right over here. So player one goes here, player two goes here, and player two has the winning strategy. What should player one have done on their turn?
Gone where player two ended up going.
Yeah, player one says, oh wait, no, I want to do over. I didn't mean to go here. I'm going to go where you went. And if that's the case, player one was able to steal player two's strategy. So this proves that player one always has a winning strategy. And I have no idea how to play this game on a large board. It's an existence proof. So, I know it's almost the end, so I just want to quickly show you what goes on. Here is essentially the start of the game board. This means I have n copies on the 1 bin, n-2 on the 1 bin and 1 on the 2 bin, n-3 on the 1 bin, 1 on the 3 bin, and so on. And what you do is you assume player one has a winning strategy. So I shade this, I don't know, do you see this as like a peach maybe, or an orange? So I shaded orange.
Coral.
So player one moves player to here, and player one still has the winning strategy. No matter where player two goes, player one has the winning strategy. So I would shade both of these the color for player one. And I keep going down this path. All of these would still be winning strategies. And now the interesting thing is I come to this point once with an even number of moves and once with an odd number of moves. And so depending on how many moves I take to get here, if we assume that this was a winning strategy for player one, this now becomes a winning strategy for player two, and I can just propagate things upward. And so I'm not going to go through all the details, but the idea is that if player one has a winning strategy, player two is able to do one extra move and switch parity. All right. So there's a lot of other things you can do over the summer. Some students, including some from Michigan, looked at what happens if you have more than 3 people playing, including what happens if you have alliances. Does the average number of moves in a random game converge to a Gaussian? How long do games take? We now actually have a lot more knowledge of that in the last few weeks. And then you can define what happens on other games. Instead of using Fibonacci's, what if you use other things? So what I hope you got from this is that if you haven't seen monovariants before, they're incredibly powerful in terms of attacking a large variety of problems. But there's a lot of work that's often required in terms of trying to figure out just what monovariant you want to look at. So thank you.
Thanks, Coach Steve. Let's give him a big hand, everybody. Here we go. There we go. Okay, I'll stop the recording. And